Let's get started. So I am very excited to be here today to talk to you all with Andrew Fikes, who is the VP and Engineering Fellow at Google, and I'll let him introduce himself, and then I'll go and talk to you about who I am.
Okay. Well, first off, welcome. I'm excited to see everyone here today. I was promised an intimate talk in an intimate setting with just a few small number of people. This is amazing. This is really exciting to me. I've worked in the distributed database space for a long time, and seeing this many people who are as excited about storage as I am, which is a hard thing to do, super geeky about it. So I'm excited you're here. First off, just a little bit about myself. I've been at Google 18 years. This is the only job I've ever had. I came right out of school and went into Google. So I've kind of grown up in the Google culture. I've grown up sort of learning things from the ground up. I was the tech lead of the Bigtable team. We have our external product, the Cloud Bigtable, which I worked on for many, many years. Tech lead the Spanner team through most of its initial development. And the last 3 years I've served in a role which is we call area tech lead, which covers, in my case, both storage and databases. And I cover basically tech lead role for everything from the disks at the bottom to a little bit of the networking in between, all the way to the distributed databases at the top. And so I know quite a bit about the distributed database space, and I know a little bit about everything else. So hopefully I'll be able to answer a bunch of questions that y'all have today and give you a little perspective about engineering at Google.
Thank you, Andrew. My name is Deepti Srivastava. I am the product manager for Cloud Spanner. My entire tenure at Google has been in Spanner, so it's a few more years than 3. Before that, I was at Oracle working in the RAC database kernel. And before that, I was researching distributed systems. And I actually never thought that databases were cool because that's 30-year-old technology, right? Who cares?
I had the same problem. I never took a database class in college because I never wanted to work on databases.
Yeah. Here we are.
And here we are.
And it's been a very exciting journey. I worked with Andrew to launch Spanner internally, and the Chris's here. There are some Chris's here too. To launch Spanner internally as a service, and Spanner has been running internally as a service, managing a bunch of critical infrastructure for like over 7 years, and it was my nuclear project to launch it, so it's very exciting for me personally to talk about the history and journey of Spanner with Andrew. Before we go further, there is a mic here. Unfortunately, we have only one mic, so as you have questions, if you could maybe make your way there, and if you want to shout it out from where you are, we'll try and not change your question and repeat it and answer. So let's get started. Okay, so first, I get to do my what is Cloud Spanner? So for those who don't know, Cloud Spanner is one of our database offerings on Google Cloud Platform. It is basically the same infrastructure as internal Spanner, and it's exposed via the Cloud API, so that's the difference in sort of the access path is different, but it was essentially a differentiated service on Cloud, on Google Cloud, because it combines the benefits of relational semantics with non-relational or NoSQL horizontal scale. So we call it our no compromises database in that you don't have to compromise between schemas and SQL and strong consistency and ACID transactions and the global scale that you get with Spanner. So today's talk is really about how this awesome product, I love this product. I call myself a database person now through my journey with Spanner. So how did this system come about, both the sort of technical history as well as some of the people history around it. And this is what we offer essentially externally on the Google Cloud Platform. So Andrew, what came before Spanner?
So when I start to tell the Spanner story, I think it's sort of important to think about where Google was at that time, right? So essentially where we were in about 2007, 2008 as a company. Google historically started as a search company and over time grew to be an ads company, a mobile company, a geo company. I'm probably forgetting mobile, a few different things like that, and eventually a cloud company. But around that 2008 time, we really had kind of an interesting set of infrastructure internally. We're a large MySQL database shop on our ad side of the world. We ran about 90 database shards and had kind of a home-built query system that worked across them. So we were dealing with sort of large-scale distributed partitioned MySQL instances. We were also a very big table shop at that time. So we started Bigtable, I want to say 2003, 2004, somewhere in there. It was really focused on the search landscape, right? We wanted to build a big table that had as its primary key the URL of a web page, and then its columns would be the actual documents and PageRank and other sorts of things on the other columns. So we had a MySQL shop and we had a Bigtable shop. We were also, however, starting to become an apps company, right? So we all know and love and use G Suite today, but there was a time when Gmail was a kind of a smaller product. And so as Google was starting to become a calendar company, a drive company, and these sorts of things, we were starting to get these needs of more complex applications being built on top of our infrastructure. And so really that was kind of the ecosystem we had at that time.
Yeah, do you want to touch upon Megastore at all? Or?
Right, so Megastore was kind of our first foray into something that looked close to Spanner, and it was an application library that was built on top of Bigtable that actually did use Paxos, but provided a much smaller kind of data partition, sort of a what we call an entity group. And it was rolled as a client library, right? So you had to link it into your client, and you had to deal with client semantics on top of Bigtable.
Yeah, so there's a paper on Bigtable if you care. There's a paper in Megastore if you care. And as these products evolved, like we know we can touch upon the journey. And if you thought that we weren't going to get technical, like we have gotten technical. So what prompted the need to build Spanner, given we had awesome Bigtable that engendered a bunch of other NoSQL systems outside, and we had Megastore, which was almost Spanner?
Yeah, I mean, I think the most obvious thing was sort of scale, and scale with these applications with things like Gmail, right? Where we were starting to think about, okay, Gmail is in 3 data centers, for example. Well, what happens if Gmail gets too big for a data center, right? How do we split it up? How do we manage the geographies that are associated with users, right? We had a large user base on these applications that was developing in Europe and in other countries, and we didn't want them to have the same latency semantics as the people in the US. So we were really thinking about this sharding concept, right? So we were really interested in that kind of geo concept. We were also starting to really think about the importance of consistency and what it actually means to have a consistent system and how it impacts our developers and our users and our productivity and velocity. And so that was sort of coming around in there. Interestingly enough, right around this time, we decided that 90 shards was enough MySQL shards, that we had resharded it, and every resharding was a couple of years, and we kind of thought if we were going to do it again, maybe we should think about whether or not we should do something different. So we really had sort of the growth of the apps and this interest in consistent replication, transactions, and those sorts of things, because users actually do notice inconsistencies. And we also had this growth on the ads sort of more financial database side to just really be able to scale to the enormous business that Google was developing.
Yeah, just to give you a sense, so Andrew's being very modest, like the ads database is how Google used to make money. So it was really important that we didn't spend 2 years plus every time we did a reshard. And I don't know how many people here remember when Gmail was like you could get 5 friends, like if you had a Gmail account that you could get 5 friends to get a Gmail account. So that scale of like going from whatever, some number of users to 7 billion accounts or whatever it is today, that's truly like the scale and the time that we're talking about here. So before we go into that stuff deeper, did you get it right the first time?
Right. So one thing I hear a lot is, how did you come up with this great idea? Like, you publish these papers, they're sort of, seminal, like, what's the process? And I think what people miss a lot externally is we spent years getting it wrong. We actually started thinking about Spanner and split off a chunk of people from Bigtable to work on it. And I think we built, and Chris can probably attest, 3 or 4 different systems over 2.5 or 3 years before we landed on the one that we ended up with. We had some horrible mistakes. One version of Spanner actually supported recursive directories. And we had RPC operations that could do recursive descents on directories. And as you can kind of see, that's really, really far away from the relational model. The good news is that when the ads team came to us, we sort of got our hands on a real customer that we were trying to work with. And when people ask me, how do you decide to build infrastructure, I think it starts with a really good customer. And for us, that really good customer was the ads database. Yeah,
customers first. So let's get into a little bit of the details and talk about how is Spanner built, sort of what are the building blocks, if you could talk to us about that. We have an awesome picture here that you can talk about, but I think that picture is super cool.
Wow. So one of the great things about building infrastructure at Google is you start with like a really great set of resources. So this is a really good example of sort of what it's like to build infrastructure in our cloud. These basically show our network lines. One of the gifts that we have as engineers is that our internal networks within the data center are phenomenally good. I haven't really worried about networking performance, network loss, for a really long time. And as a storage person, that means you can take a whole set of things and just set it aside. And you can think about the algorithms and things that lay on top. That same internal experience we get across large spans as well, right? We have 3 redundant lines out of data centers. We have extremely high availability. Being able to depend on that level from your network really simplifies a lot of your distributed system building.
Yeah, and I know it says it there, but anyway, the blue dots are basically where GCP, so Google Cloud, has presence externally, as well as the number indicates sort of how many availability zones there are and how they're all connected via Google Fiber, essentially. So to Andrew's point, when customers ask me, like, well, what will the latency be like for this globally distributed massive thing? I'm like, not very much. Like, they're like, how do you go over WAN? And like, we're like, we don't have to go over public internet for the most part. So that's super awesome. I wonder if you want to touch upon Colossus before we go to the next thing.
So I think the other area we've always really depended on is we do have a very large-scale distributed file system that sits as sort of the basis of all of our distributed storage systems. We published a paper on GFS, which was the very first version of that, I think probably in 2002, 2003. The one we use now today is actually called Colossus, and it basically occupies, many, many megawatts of power of footprint of space. And we really depend on that for all of our write operations. And so that means the durability of the data, for example, is something that we can delegate down. It also means that we're in an environment where we can disaggregate compute from storage, right? It gives us the ability to respond to hotspots on one server by actually picking that piece of, indirectly picking that piece of data up and moving it to another server while leaving the storage beneath. Fun little fact, Colossus is actually built recursively on top of Bigtable. So this is a place where we're reusing our infrastructure in order to be able to scale it out.
There's the amount of virtualization that's happening in our infrastructure stack is pretty astounding because, again, customers ask me, what happens when a disk fails? And I'm like, I haven't thought about a disk failure in I don't know how many years, so.
Yeah, and I think this is when I spoke earlier to now getting a lot of visibility from everything from the disk layer on up, Google actually, builds its own disk appliances, right? And we spend an enormous amount of time thinking about the availability of a disk appliance, the cost of a disk appliance, how fast we can execute RPCs against these things. We continually improve our efficiency and effectiveness of those disk appliances, and we deploy them at massive scale. And sort of being able to have that sort of incoming pipe of people working on even just the building raw components that you're building these systems on is just it's an absolute luxury.
Yeah, I think we're a hardware company too, as much
Absolutely.
Data center business. So this is the other part that we basically win on, which is true time. So walk us through this.
Yeah, so I can't be more excited to show you this most boring rack. I think one of the most interesting comments I usually get when people read the Spanner paper is they're like, wow, atomic clocks. And then you're like, yes, you can get them on eBay. They're not as expensive as you think they are. This is actually our latest generation. So this is rolling out into the fleet now. The TrueTime team is a really small group. This basically shows a fairly standard configuration that we have within a data center. There are 4 time servers in here. 2 are connected out to the GPS antennas that you see. This provides a GPS calibrated signal. 2 of the other remaining servers are actually connected to 2 atomic oscillators. There are 2 different brands of oscillators here, so we get different failure behaviors, actually in the same with the GPS cards as well. And this is connected into our fabrics. And what this does is it provides a really accurate time signal with bounds. And this is sort of the principle upon which Spanner is built. This idea of not just saying a point in time, but an interval in time. And what can we do with a very highly reliable, accurate interval of time? And that's what TrueTime provides. And I can't speak exactly to where we are now, but it's clearly less than a millisecond of drift. There you go.
Yeah. This is one of the sort of cornerstones that allows us to be the differentiated technology in terms of external consistency, and we'll get into that. But I think it's important to understand that it's not just about atomic clocks and GPS, but about the hard work that goes into building these systems and the infrastructure around that. Okay, so let's quickly touch upon, given those building blocks, how does Spanner do a serve request, right? What is the life of a read and a write? I am very excited to say that Andrew actually drew this by hand. He's good with crayons. And his writing is remarkably good, right?
I went to an engineering school. So yeah, my kids actually helped me with this. It was great. We did it this weekend. It turns out that even an 8-year-old can design a distributed system. Hers didn't look quite as good as mine, but we will take it. So we do get a lot of questions about how does Spanner work? What exactly happens when I issue a read or a write? So typically what I like to walk people through is the life of a read and the life of a write. At kind of a high level, you can see it here. I think it's easier to start with the life of a write. We have a client. These are typically in a VM, although they could be other places. They go to our load balancers, and from there they go to a front end, which sends them on to the very first span server. The span server is what actually stores, be a good description of this, slices of your data. So we refer to them as Paxos groups. These are basically data containers that are spread across multiple zones for availability. Commits have to go to 2 out of 3, or 3 out of 5, or some number that forms a quorum. As you can see it here, the span server in zone A will take that write that it gets, and it'll forward it on to zone B and zone C. It will wait until 2 of those come back, or 2 total come back, both its local one and one of the others, and then it'll return back to the client. And that's the point at which it becomes durable. You can see in reference here Colossus, which I mentioned earlier. This is our big distributed file system. Span servers, we run tons of them. Internally, Spanner is heavily used. So we're talking about thousands to tens of thousands of these running in a data center. Your data resides on a fraction of those.
Before you move on to the reads, really quickly, just to level set, because we live and breathe this, so Spanner is a synchronously replicated database. What that means is that we have full copies of the database data in at least 3, if not more, availability zones. The copies of data are in Colossus, which is the distributed file system that Andrew talked about. And because we have disaggregated storage and compute, span servers here are the compute units that act on the data. So the questions around, well, what happens if a server goes down? Do you have to reload all the data in memory in a different server? Are kind of orthogonal because the data is always in the storage layer, and all these compute units or span servers are doing is being responsible for serving the data, right? And so when Andrew talks about sort of a client sends a write, what they're doing is they're saying write key with value X, and that means that there's an operation that needs to happen. And any one of the compute units, this is really important, right? Any one of the compute units can pick it up. We use Paxos to figure out who the leader is. We don't have a concept of master. And there's a paper out on Paxos. Essentially, it's a group consensus protocol that allows you to choose at most one semantics, essentially, for a given point in time or a given sort of operation. Does that summarize it okay? But I just wanted to make sure we understand what we're talking about.
Yeah, I mean, I think the other thing that's happened, a few other things that are happening here is, during writes, we do use true time to pick a timestamp. Those timestamps are used to create an ordering, which we talk about as being externally consistent, right? That means that, if you do 2 successive operations, they will get increasing timestamps, right? So an operation that happens after another operation by the concept of time will actually happen that way. I think the other thing that's kind of interesting from this diagram is really to think about, where does high availability come from, right? And high availability really comes from the fact that we are replicating data, right? So, for example, if zone C falls off the face of the map, earthquake, California, that sort of thing, we can still continue to issue writes to zone A or zone B. If we have a crashing bug in one of the span servers, for example, the other ones can pick it up. And so you get high availability by taking these components of kind of blast radiuses and what happens when they fail and making sure that you have other things to capture them up.
Yeah, do you want to walk through the read?
Yeah. A read is also very simple. I drew it here showing that the reads don't necessarily have to go to the leaders in order to be strongly consistent. So a client might do a read. He might go to one of the other replicas of the individual group. Now, when he gets there, he has to, he basically picks a timestamp, which is what we call now plus epsilon, which is typically the time at which we know no writes that we could have seen were committed. That front end will basically say, OK, pass it on to a span server. And the span server will say, OK, do I have all of the data up to that time? And if enough time has passed, because we're talking, order milliseconds, and, writes may be going on, he will actually just return the data then. If he doesn't have the data, he'll reach out to the leader and say, dude, I hear you have some data for me. And the span server will say, yes, here you go. Either here's the data you need, or you actually have all the data. I just haven't told you that you have all the data. And in that case, the read will be performed locally.
Yeah, so I think the point here that is different from other systems is that we are, in almost all cases, serving the data from the local replica. Yes. So we're not, there are other systems that ship buffers around when they're replicated. We're not shipping buffers around, right? What we're saying is, hey, what's the latest timestamp that I can serve data at? Do I have it or not? And if the answer is yes, you have it, then you go serve it, or you wait for the data to be shipped as part of the Paxos protocol separately. Right, so you're not actually shipping megabytes and megabytes of buffers around. Yeah,
and just to give you an order on sort of the timing here, you could imagine that zones A, B, and C are actually all within a region. In that case, your writes are on the order of 5 to 10 sort of milliseconds, because that's sort of what it takes to create a quorum across those data centers. For a read, it would be much, much faster because you're only reaching out to one data center. So once we get through the load balancer and everything like that, I think it's in the 3 to 5 range from external cloud.
Yeah. All right. So let's talk about some of the aha moments where we, well, you at least, chose to be a distributed systems guy. Sorry, to a database person from a distributed systems person, right?
Yeah, I mean, so I think, people say, well, what's great about Spanner? What should I take away? I think there are 2 things that I typically reference. One is that as a distributed systems engineer, you're grown up and everybody tells you you cannot trust time. The clock on your server is absolutely something you can't trust, right? And you develop sort of this innate fear of that thing, right? It's like legendary. And you also sort of probably experience some really bad things when you decide to trust time anyways.
Bless you.
Having the ability to actually trust time, and we are now 10 years later, and I can tell you that I completely trust our time system, right? It has made my life so much easier. Being able to basically have a source of global ordering that I don't actually have to reach out and talk to, that I can reference locally, is a huge, huge, huge just thinking shift. And it took us actually quite a long time to get over that. When I said we did 2 or 3 versions of this system, some of the earlier ones actually worked more on logical clock passing or figuring out how to weave these things through. And weaving timestamps through your system actually has some really bad effects usually on your client. You're like, okay, well, this person can give me a timestamp. Now I can take this timestamp and give it to someone else. That means that the application actually has to see it. And so being able to trust time and use that in a way actually has really good upper-level API effects as well. The second sort of aha moment was that we spent a lot of time not implementing transactions in Bigtable for a variety of reasons. And the main reason is that the availability of any one of our Bigtable tablets was not sufficient enough to support transactions. And so what Paxos and groups bring us is they bring us highly available participants. So the other sort of aha moment in here is you can do a lot with highly available participants. You can trust them to be coordinators. You can trust them to hold locks. You can trust them to do things like that. So it's really the combination of both trusting time and having highly available components upon which to build transactions that make Spanner unique.
Yeah, I remember get time of day was an evil thing and you never put it in your code. But true time, along with Paxos, gives us that external consistency of you can, and I love saying this to customers because they're like, I don't believe you, but you can write from anywhere in the world into a Spanner database, and you can literally say, I wrote, like I incremented my bank account with $50, and anywhere in the world, somebody can read that timestamp and actually get an answer for it was plus 50, which is an amazing thing to have. So
yeah, $50.
Yes, it's better than 0. Okay. So let's move on to a little bit more on the nostalgia piece, which I find exciting. But we talked about scaling systems, but you also have to scale teams.
Yeah, I mean, I think every good project, and I talked to some people earlier with sort of small teams. Spanner, of course, started with a small team, right? It started with 4 people in an office. I think this picture is in 2012. It shows about 5 or 6 people. We look heavily engaged in a particular event, probably, in terms of a server going down or us debugging sort of things. It's kind of fun to look back.
Yeah, so
Chris is down here in the front. He looks much younger in that photo.
There were less critical systems running
Yes.
on Spanner at the time. And I also want you to talk about this one.
Yeah,
Super awesome.
This was my cube mate. This is Mike. He's a fan of ASCII art. These were our first 100 users. So every now and then you see a $20 bill posted on the front of a deli or something like that. This was our screen as we watched internal users adopt Spanner. And when we hit 100 on our lovely VT320 here, we had a little party.
I was actually there for this one. So I want to have people look at this and then this.
Yeah, so a couple years later, we're getting a little bigger. We added a few fish into the mix, as any good team has. And a few of them, I think, are still kicking.
Andrew and I commissioned this logo because, of course, we were a service and we needed a product even,
Yeah.
and we needed a logo. So we had this logo. And if you don't understand what that is, it's obvious.
It's
this
a
is
spanner.
a spanner turning Google. So, and then.
Yeah. So this is actually a couple of years ago at this point. I think the key thing to take away from this is that building a distributed system that is as highly available and actually has all of the features that you all know and love is actually a relatively complex problem. The other thing that I've really grown to appreciate is that database problems and systems problems are actually full stack problems, right? And so you have to have the amount of complexity that is in these systems now is substantially more. When we built GFS in the early days, which was our first distributed file system, we almost decided not to do it because we thought it was too complex and nothing that complex would ever work. It turns out it's the simplest thing we've ever built. And Spanner has many more ages of complexity on it. I think the other thing you can see in this picture is this enormous giant wrench in the background. That actually is used for trains. So if you ever need to change a train wheel, we have a wrench for you.
Yeah, we actually have 3 of them because we don't.
We have 3?
Yes.
Okay.
We have 3 wrenches on 3 different sites. And I think the takeaway, because we are highly available.
Yes.
And replicated. So the thing for me was, because for me, this has also been a journey, and building teams to have that sort of rigor and mindset when we're doing infrastructure, that we have to have, we make no compromises, we don't cut corners, and the processes for around that stuff is, it changes, right? Like 5 people, the process that works with 5 people, which is nudging people to say, hey, fix this bug, versus 50 people versus more than 50 people is different. And so it's really been an exciting journey, and Andrew is very, and I am as well, very excited about the culture and the team cohesion and all those things. And they're real things, you really have to worry about culture and respect and all that stuff as you grow people. And of course, in case that wasn't obvious, we actually have Spanner people distributed in multiple areas too. So
we have people in New York, the Seattle, Kirkland area. A good portion of our operations staff is actually in Sydney, where I think
Boston
they're just
now.
starting to wake up, and Boston. And managing a large team, finding good chunks of work for them is definitely a challenge.
Yeah, okay, so let's go into the more fun parts, which is let's opinionate.
Okay.
So let's touch on a few things that I know customers have talked to me, and I know that you're also passionate about. So first of them is CAP theorem. So does Spanner break the CAP theorem, Andrew?
This is a great question. I think for years I hated the CAP theorem. Then I started sharing an office with Eric Brewer, and he turns out to be an absolutely nice guy. So it's great. And I think as I talk it over with Eric.
Eric is the author of the CAP theorem,
yes,
by the way. Also wrote a paper on how Spanner doesn't break the CAP theorem.
As you talk things through with Eric, what his real point here is the CAP theorem was really designed to help you think. And it's really also designed for you to think about the extremes, right? So it's really about 100% situations. And in real life, nothing is 100%. And so when you really look earlier when we talked about things like the building blocks that we have, our network, our file systems, and various other sorts of things, we're able to take things like partitions, which might be really common in most people's networks or most people's WANs, and say, hey, can we think about these things different? Can we actually look at the data and understand how often partitions actually impact things? When a partition happens, for example, does it also impact the end application? Or would it actually impact the quorum? And so as you start to look at these, both from a mathematical perspective, the probabilities, but you also look at the on-the-ground data, what you find is that partitions are actually much, much less likely than the other sources of error in your system. And this is one of the arguments we made about true time, with it being more accurate than CPU failures. We can sort of make it here. It turns out that most sources of unavailability in our system have things to do with users. I don't know how many MapReduces have been run in the world that have taken down a system they weren't supposed to. They have things to do with our SRE teams, missing a comma, turning it into a period, something like that. So it's those sources, and operator error is actually much, much lower than user error. Those sorts of events happen much more than partitions. And so once you basically say, okay, let's assume partitions are not going to be the source of the unavailability, can you build a system that actually has really good availability and gives you consistency? And so that's sort of where we land.
Yeah, so I think we trade off partition tolerance for availability, right? Mostly. Cool. So the other interesting thing here is, Spanner evolved from a NoSQL sort of big table world into a fully SQL database. And so, how has your thoughts on NoSQL to 3SQL evolved?
Yeah, so many years ago, I was invited to give a talk about NoSQL. I knew nothing about NoSQL, so I went and read Wikipedia like a good person, and it said, a series of distributed systems as created from the lineage of Bigtable. And I said, oh, okay, I know Bigtable. Maybe I do know something about NoSQL. Typically, when people talk about NoSQL, they're talking about a horizontally scalable key value system, right? Typically, they also talk about some properties around eventual consistency. I was, for years, a huge fan of eventual consistency. I built Bigtable's first replication system. It was eventually consistent. I was totally convinced that anybody who wouldn't want an eventually consistent system was wrong. I'm here to tell you I was wrong on leaps and bounds.
We got it on tape.
Yes. What you sort of learn over time with an eventually consistent system is you actually go to start to work with users, right? And you see users try to build applications on top of an eventually consistent system. Yes, it's kind of fun, right? We get to use that part of our brain that creates a complicated algorithm that only works under these certain situations, and maybe the user sees it this way, or maybe the user doesn't see it that way. But at the end of the day, it's just not really any fun, right? And our goal is to build products, right? Our goal is not to build, complicated algorithms that, fix little edge cases, right? We want to get a product in front of our customers. We want to see that product quickly and get feedback on it, right? And consistent systems give you that property. I sort of had the same idea around transactions. The very first versions of Bigtable, for example, have a complicated split and merge protocol in them. We kind of knew what we were doing. We hand-rolled our own transactions. I think we did it 6 times because we got it wrong time after time after time, right? Having primitives around consistency and transactions as building blocks are incredibly productive. They let you sort of leverage those things onto other things. Mm-hmm. I think, the other thing that you find in sort of this kind of NoSQL versus NewSQL debate is really this idea of SQL. SQL's great. I think it's a perfectly fine language. Tuples are great. I think types are incredibly useful. We've seen systems on the key value space adopt types more and more. As we start to think about moving compute closer to the data, which is a trend, then things databases have been doing closer to years, you really need a language to express that. You need to understand types so you can drive it down to the processor level. Mm-hmm. And so SQL is a great language. I think where SQL tends to get a bad rap is it's often associated with vertically scaled systems, right? Things that only fit in a box. Or, they have challenges around multi-tenancy. I think Spanner does a much better job on the horizontal scaling aspect, so that gives us some power. We've also always run in a multi-tenant environment. Google has tens and 20s and hundreds of thousands of databases internally, all competing for the same resources, so multi-tenancy has been a core component of what we do for years. And so those sorts of properties of SQL systems, we kind of can look at slightly differently.
Totally. So we talked about consistency, we talked about SQL, NoSQL. How do you think it kind of comes together to power Google's cloud offerings, right?
Yeah, so, I think there's, Spanner is a workhorse, right? We use it in many, many different ways at Google. We use it both for things of scale, right? So things that are petabytes that look, kind of like traditional indexing and batch workloads. We use it for very critical high availability loads. I was just at a talk right before this where it was performance benchmarking around VM boot up times, right? And it was talking about the complexity of programming the control plane. That control plane is done in Spanner, right? So our ability to spin things up quickly and have them highly available is dependent on Spanner. We see it in sort of the, SaaS application space, right? Where you might take something like Gmail, where it takes a whole bunch of users, maps them into a single database, and gives them power that way. And we also see it in very traditional database workloads. We use it for some of our capacity planning, for example, our capacity delivery systems. And so we really have a workhorse of a system that really goes from everything from the very big to the very small.
Yeah, we actually have a lot of small use cases that are all using Spanner mm-hmm. for its manageability and scale insurance and all that stuff. So,
and it's also probably a good time. I know Deepti mentioned it earlier, which is tomorrow my colleague Dennis from the GCS team, which is our Google Cloud Storage, is going to present how GCS uses Spanner for its metadata. So our really large-scale systems are actually built with Spanner as its backbone.
Yeah, that's going to be Spanner Internals Part 2.
Yes.
Tomorrow morning. So come watch us. But yeah, it's cool to see both the GCSs and the Gmails as well as the drives and a bunch of other small internal systems like supply chain management use Spanner. All right, so these are some of the headlines for when we launched Spanner. There were more controversial ones that I didn't put here. But I know both you and I have thoughts on sort of why we launched it externally. So why don't you?
Yeah, I mean, I think one of the great things about why I'm excited about cloud, it's new workloads. I mentioned, why I get excited about infrastructure. It's because there's new challenges, new workloads, new customers. I was very excited to see examples of workloads that I saw internally, externally. I think Spanner is a great building block for a lot of applications. Being able to get that out to y'all and have you working into your systems was a big win for me.
Yeah, I think it was a while before we could convince ourselves that we wanted to be a public product, primarily because we didn't think that externally people had the same challenges that we had internally. And I remember sort of doing a whole initial program of going out there and talking to customers to see what was, like, whether this would be a useful system for them. Because at the time, this is like 3 years ago, which is dog years in cloud world, when we were trying to launch Spanner, we were cognizant that people don't want just another cool tech because Google built it, right? It's, especially on the databases side, like, people want something that solves their problems, and is this something that is going to solve their problem or not? So we actually wanted to be cognizant of user issues and see if this could solve, our user and customer pain points. And after serving customers, we found that, customers were coming to this with the new internet age of everything connected, everything always on, everything online. Customers wanted that kind of scale insurance with horizontal scalability and strong consistency and relational semantics, and so it was like a really good time to be in the public eye. So thank you so much for your time again.
Yeah.